Just a joke. Okay.
Ok, ya
Thank
estamos
you
en
very,
línea. Ok,
thank you
empiezo.
very much, Professor Antonio, for accept the invite to talk for us today. Well, Professor Antonio is professor from the Institute of Física of the Federal University of Rio de Janeiro. He is a very expert professional in atomic physics. He had supervised some students and PhD students, master science students until undergraduate students. He'll talk for us today about ultrafast dissociation of molecules. Antonio, you have 1 hour to talk for us and in English, Spanish, Portuguese, Arabic, Korean, etc. Go ahead.
Okay, good. So good morning, everyone. I thank you, Isaias, for this invitation and for the introduction. I will try to speak in English, but I prepare my presentation in Portuguese. But I see that there are some people who I think is not familiar to Portuguese or Spanish. I will try to speak English, but eventually I may switch because I don't know. I was not prepared to talk in English. So today I'm going to talk about ultrafast dissociation of molecules. I understand that most of people here, the audience, works in a condensed matter phase, but I'm a gas phase guy. My experience is 100% in gas phase, so I will talk about ultrafast dissociation of molecules in a gas phase context. I mean, one single molecule. But I think most of the ideas can be used in a condensed matter as well. So my talk is just, okay. The concept I prepare my talk according about following those topics. At the beginning, I'll try about a little bit of introduction, talk about my motivation to study ultrafast dissociation and molecules, and then I'll present and review the Born-Oppenheim approximation that usually we learn in atomic and molecular physics, most in undergraduate or graduate courses. And then I move to Martin-Auger effect, and finally I show some experimental results. Well, my motivation, I will talk mostly about molecules of atmospheric interest. And the motivation is that most of those molecules contain halogen atoms, for instance, chlorine, and they can create the atmospheric ozone. For instance, dichloromethane, one of the molecules that I'll show some results, was not included in the Montreal Protocol. So the use of this molecule can postpone the recovery of atmospheric ozone. So most of the molecules are of atmospheric interest, even treating the atmospheric ozone or the global warming. Okay. It's a little bit slow. Sorry. Okay. So in this slide, I'll show you the Born-Oppenheim approximation. I'm showing you an example of a diatomic molecule, AB, with some electrons. So there's the center of mass of the molecules. Ra is the position of the nucleus I, Rb the position of nucleus B, and R1 and 2 are the position of the electrons. And I define the R, the capital R, as the internuclear distance, which is the difference between these two vectors. and the reduced mass of the system, where Na is the mass of nucleus A and B, the mass of nucleus B, and the Hamiltonian of the system, we can write with those three terms. The first one is the kinetic energy of the nuclei. The second one is the kinetic energy of all the electrons. And the third one is the potential, which includes the interaction of the electrons, of all electrons with nucleus A, the interaction of the electrons with nucleus B, the electron-electron interactions, and the repulsion between those two positive charged nucleus. So this is the Hamiltonian. And usually we can separate the Hamiltonian in the nuclear part and the electronic part. And the most important is the reduced mass of the system of the two nucleus. It's much larger than the electron mass. So the kinetic energy of the nucleus can be, the nuclei can be considered as frozen during the electron transition. So as a result of this approximation, because of the reduced mass of the nuclei are very large, the transition takes place vertically at a fixed nuclear radius, internuclear distance. So this is the Born-Oppenheim approximation. But sometimes, in the case of ultrafast dissociation, there is a limitation of this approximation. This limitation is not applicable. So in ultrafast dissociation, we have a deviation of the Born-Oppenheim approximation. So I will talk also about the Meitner-Auger effect. Usually it is called Auger effect after Pierre Auger. But 1 year, in 1922, Lise Meitner discovered this effect. But unfortunately, the effect was named after Pierre Auger. But in the last few years, in the literature, there is a movement that wants to grant to Lise Meitner this discovery, and the former Auger effect is also called Meitner-Auger effect, or sometimes Auger-Meitner effect. So, and in 2 years ago, in 1922, we had this 1 year of discovery of Lise Meitner discovery contribution to the Auger effect. So I wrote with my colleagues from Rural University, Viviane Morcelli, and from Bahia, Professor Ferreira. We wrote this pedagogical paper about the contribution of Lise Meitner, and then we should grant the credits to her also as well. So, what is the Meitner-Auger effect? First of all, here at your left side, we have the direct photoionization, the photoelectric effect, which was described by Einstein in 1905. So the direct photoionization, we have one photon who incides in the molecule and the system is absorbed, and one valence electron is ejected with a kinetic energy. And this kinetic energy is basically the difference between the photon energy, which was deposited in the molecule, and the binding energy. So this is the direct photoionization, or the photo effect. But when you go to high photon energies in the shallow or deep core of molecules, we can the photon has energy to eject one inner electron, so the photon can eject one in electron from a deep shell. This is ejected, so you have the photon electron, but this vacancy is filled by an outer electron, and then the excess of energy is released as a second electron, the Auger electron. This is the Auger electron. So instead, we have the photoelectron and also the Auger electron. The difference is that the Auger electron have a constant energy, which is basically given by the structure of the molecule. The photoelectron, its energy depends on the photon energy, but in the case of the Auger electron, the energy is constant. This is the so-called normal Auger decay. But on resonance, we also another kind of Auger process is also is a resonant Auger, and we have two kinds of resonant Auger: a participant Auger, where the initial electron is promoted to an occupied orbital, and this electron decays, again, the same electron which was promoted decays, a second electron releases as an Auger electron. So this energy is basically like the photoelectron energy, so depends on the photon energy also. And the second electron in the second process is the spectator Auger. In this case, the electron which is promoted, excited to an occupied orbital, and stay there as a spectator, and another electron decays, and a third electron is emitted as an electron G. So this is the so-called spectator Auger. So this talk is about those two, about the expectation, the resonant Auger effect. So what is the difference between ultrafast dissociation and the conventional dissociation? In the conventional dissociation, we have the photon, which is absorbed by a molecule, diatomic in this case. The molecule is excited in a resonant phenomenon, and this excited molecule then emits a resonant Auger electrons and get singly ionized. And then in the second step, the dissociation takes place. This is the conventional dissociation. But in some cases, the ultrafast dissociation takes place. The first step is the same. The photon is absorbed by the molecule, and then this excited system then dissociates, and the whole remains in one atom, and then this atom decays and releasing an Auger electron, and this Auger electron has an atomic character. In the first case, the Auger electron has a molecular character. So this is also an explanation of ultrafast dissociation. And the coreonization of molecules, we use usually soft X-rays, and results in a core hole creation. And the lifetime is about femtoseconds. And the time of the hole is about femtoseconds, but sometimes in the ultrafast dissociation, this core hole time is the same order of magnitude of this dissociation time. So the dissociation time, we can calculate it classically. So if you know the potential energy curve, we can calculate the time which the molecule can dissociation is a simple formula. This is classical. And in the ultrafast dissociation, the dissociation time competes with the core hole time. So when the dissociation takes in a molecular Now, in a molecular decay, we have usually some broad features in the electron spectrum. So we have some disbroaded because the curve here, the potential curve here is, has some dependence on the internuclear distance. But if the dissociation takes place at very large distance, internuclear distance in atomic character, the peak, the Auger electron peak is usually sharp, very sharp. So this is one of the characteristics of the ultrafast dissociation. So it's beyond the Oppenheim approximation. So the Born-Oppenheim approximation is not valid anymore. So here so we have some example, some results from the literature for a small molecule, because you know the dissociation time here depends on the effective mass, the reduced mass of the system. And if the reduced mass of the system is very small, the dissociation time is also small. And if the reduced mass is large, the dissociation time increases. So they use here a small molecular diatomic molecule, HCl, and you have and we have here a XPS spectrum, and you can I can show you some features of this spectrum. We have some photoelectron peaks. This peak is moving as we change the energy of the photon, so we can easily recognize that this is a photoelectron. But the surprise are those structures here, the singlet S, the singlet D, and triplet P, which are signatures, not of the molecule, but of the Cl atom. So here we have an evidence of ultrafast dissociation of this molecule, where the photon absorbed, the molecule resonantly absorbed, the molecule excited, then it takes place, the ultrafast dissociation, the whole, the chlorine atom keeps the whole, and then it is ionized, and this electron has a atomic character because it comes from the chlorine atom, the excited chlorine atom, and not from the molecule. So we have this spectrum, one dimensional and b-dimensional. You can recognize all the electrons. This is those lines, those three lines are the photon electrons. We have here some resonant Auger lines, and above the chlorine edge, you have also the normal Auger, which has a constant energy, kinetic energy. So this is an investigation of the resonant photoionization, and the results shows an evidence of ultrafast dissociation. So again, the same, and just showing here, the authors compare the HCl with the DCl, which has a larger reduced mass. So the idea is compare those two systems, which are electronically equivalent, but because they have different effective reduced mass, the dissociation times changes, even though the structure is the same. It's just a max effect. So the idea is to compare the HCl with DCl, which are very similar systems, but with the association times very different. So the same aqui, the Auger, the constant Auger, which are those lines aqui, the resonance and the photoelectrons. Well, but the question here is, we saw that the ultrafast dissociation take place when the reduced mass of the system is small, because the dissociation times is also small. But does the ultrafast dissociation takes place in heavier molecules, or what's the limit of ultrafast dissociation? So what I'm going to show you is extending the results to larger molecules and try to see if the ultrafast dissociation takes place or not. So this is one of the experimental apparatus. So as I said, I work in a gas phase. The first part of the experiment took place in the Brazilian synchrotron. And we use a time of flight, a conventional time of flight. So we have the beam here, the photon beam, and then a gas jet. The beam ionizes the molecules. There is an electric field that pushes the positive ions to the right and the electrons to the left, and we got a conventional mass spectrum. And the time of flight, by measuring the time of flight, we can identify the fragment, because the time of flight is proportional to mass to Q ratio, mass to charge ratio. So this is the results for the methylene chlorine. And we basically we measure some mass spectrum, and we change the photon energy, and we studied how the peaks, the intensity of the peaks change when we go from the valence, low energy, to the core, to chlorine 2p core. So here on the upper part, we have the yields, the ion yields of some fragments, and see how they change when we change the photon energy from the valence to the core, to chlorine 2p core, and we see some changes in the fragmentation pattern. And here, near the chlorine 2p, is where we can look for ultrafast dissociation. So in fact, we found some evidence of ultrafast dissociation by measuring the kinetic energy of the recoil ions. So in red, we have the photon absorption, the total ion yield, which is mimicking the photon absorption. We have the two resonant structures, 2p, chlorine 2p, 3/2 and 1/2. And we measure the kinetic energy of the chlorine atom, and see that when we get closer to the resonant, the kinetic energy decreases and then increases again. And you can understand that by using the ultrafast dissociation. So our proposal is that the photon is absorbed, resonantly absorbed by the molecule here in this resonant phenomena. Then the excited molecule then dissociates, releases one of the chlorine atoms, which takes the whole, and then the chlorine releases the OG electron. So this electron takes most of the energy because of the mass. Momentum conservation, this electron, which has a very small mass compared to the chlorine, takes most of the energy. So in a resonant phenomenon. So if it takes most of the energy of the chlorine decreases. So we observe this minimum in the resonance. So this is a piece of evidence, but we cannot say for sure that in fact that ultrafast dissociation, but this is an evidence. And in order to get to be sure about if ultrafast dissociation is taking place or not, we move to another laboratory. This is the Canadian Light Source, where I spent 1 year in my sabbatical year in 2016. So I spent 1 year there in the PGM beam line, and this is me in the chamber. This chamber has a toroidal spectrometer where we can measure the kinetic energy of the electron. So this is the direction of the incident photon and the interaction region, and in this toroidal spectrometer measure the kinetic energy. We have some detectors here, maximum position sensitive maximum phase detectors, and we can then study in a more appropriate way if ultrafast association is taking place or not. So those are the results. We studied the CH2Cl2 and the CD2Cl2. The idea is to study two similar systems. They are electronically equivalent, but the reduced mass are slightly different because of the deuterium atom is heavier than a hydrogen atom. So we measure the total ion yield, which mimics the photon absorption. So we have the total ion yield of CH2Cl2 here on the left side, upper left side in red, and same a very similar spectrum for the CD2Cl2, the same structure, same energies. The system is equivalent electronically. So we choose those resonance, the first one, 2p3 and 2p1/2, to look for ultrafast association. So we have the Auger spectrum, and this one on your right side, bottom right side, is the spectrum for both molecules, CH2Cl2 and CD2Cl2, at this first resonance, and here the same spectrum for both molecules at second resonance. And in the first resonance, this one, 2p3/2, we can see some evidence of the peaks which energy matches the energy of Auger electron of the chlorine atom. So this is, in this case here, we see in both molecules, CD2Cl2 and CH2Cl2, these orange peaks here, they are signatures of atomic decay. So we can see that in both cases, in both molecules, ultrafast association is taking place, but only on this resonance. If we move to the second resonance, we don't see those peaks anymore. We only see molecular Auger decay. The ultrafast association only takes place on this peak here, which has a very repulsive character because it's a sigma star. It's very repulsive. So ultrafast association takes place in this resonance, but not in the other one. So, and that is so, as I said, the dissociation times competes with the core hole time, but the dissociation times depends on the reduced mass. And in the case of CD2Cl2, the reduced mass is a little bit larger, so the dissociation time is a little bit larger for the CD2Cl2. So we expect that the heavier molecule has less ultrafast association. And that's in fact, we measure the intensities of atomic in red and molecular decay. Atomic here means ultrafast association. And we see that in the case of CH2Cl2, 36% of the events takes place as ultrafast association. In the case of the other molecule, only 25. So this is also evidence of ultrafast association, and we see that the effect of the reduced mass of the system, that is changing the intensity of the ultrafast association of the atomic decay. Then we move to a heavier molecule, the chloroform, CHCl3. It has one chlorine atom more, so it's heavier, so the reduced mass is even larger, and we're still looking for ultrafast association. So, but the intensity of ultrafast association decreases a lot because of the reduced mass increases, but we still can see some evidence of ultrafast association. These orange peaks here, they are small in the country, but we can still see some evidence of ultrafast association, but the intensity is much less. It's about 15% in this case. So but it still can observe ultrafast association in heavier molecules. So And now moving to a different molecule, the SF6, which is very important for the global war. It's a very important molecule. Has a global warming power 1,000 times larger than the CO2, which is a conventional molecule for global warming. So the SFCs also contributes to global warming, and that was motivation. So we study fragmentation of this molecule in a high energy using photons around the S1s resonance. And here we have the total ion yield spectrum in a log scale. His small shoulder here is in fact a forbidden transition, because the initial state, the final state they have the same symmetry. So since they have the same symmetry, they are dipole forbidden. So this is a dipole forbidden. It takes place only because of the vibration of the molecule. When the molecule is excited, it activates some vibration, and the vibrations change slightly the geometry of the molecule, allowing the transition. So we see a small contribution here, and you see this huge peak is allowed transition from the ground state to the 61. They have different symmetry, so this is allowed transition, and this small one is a forbidden one. But interesting, this is the mass spectrum of the molecule at this photon energy, but it's very interesting that we see at this forbidden energy, which is very weak, but the mass spectrum changes dramatically. For instance, we see that the single ionized sulfur ion increases at this forbidden resonance and then decreases again. The F2, this double ionized fluorine atom, decreases intensity in this resonance, the forbidden resonance. And we see the same phenomenon the other fragments too. So this is very small resonance changes the fragmentation pattern. So we want to understand what's happening. So we published this paper when we observed strong selectivity in symmetry forbidden vibronic transition, deep core ionic fragmentation of SFC's molecule. Then the idea was to move to another synchrotron, to another facility. We moved to Soleil, we in a collaboration with the Maximum group from University Sorbonne, and they have a beam line there. And we studied the resonant Auger decay, subsequent the symmetry forbidden transition. So this is a bidimensional Auger spectrum. We have the vertical scale shows the photon energy, and the horizontal scale the kinetic energy of the electron. And we see here the intensities at this energy 2482 is a forbidden transition. We see a small intensity of this resonant phenomenon, and the allowed transition, which is much stronger. But in this paper, we focus on this small resonance, this forbidden resonance, and try to understand what's happening there. So on your right side is the same spectrum. We just is integrated. We integrate the signal at this photon energy, and so we have the kinetic energy of the electron, the intensity at this energy, at this photon energy, with some peaks here at this forbidden transition. And the idea is to study the dynamics of photoexcitation following those peaks. And that is what I'm showing here, the same spectrum here. So we choose some peaks, some resonant peaks, some OG peaks, and we measure both the width, the intensity of the peaks. By changing the photon energy, we see how the intensity of the peaks change. And also the position of the position of the peaks also change. We can observe this very strange S curve here, and also the peak width, which is it gets narrow on the resonance. So this is a very interesting results, and this S shape here shows the limitation of Born-Oppenheim. How we understand this shape? The peak position is changing with this S shape, and we can understand that by energy conservation. When the OG electron is released, so part of its energy is shared with the nuclei. So the nuclei changes also, and the positions of the so the nuclei changes, and the energy of the OG electrons changes a little bit. So we can see this S shape, which is an interaction of the energy share between the OG electron and the nuclei. So, and this also some evidence that very fast phenomenon, the association also is taking place in there. So that's the idea to study this molecule. So now finish those work I did alone. I have some collaboration. I have some people who collaborate with me. For instance, Professor Viviane Morcelli from Federal Rural of Rio de Janeiro. Victor Bonfim was a former postdoc. George is my postdoc today. I have a PhD student, a former master's student, and also have collaboration with people with former students, PhD students, and master's students, and people in Brazil and United States and Canada. So I have a theoretician from the chemistry department at my university. Marcelo is in Aline are my experimentalists who collaborate with me. I have some people from Canada, also Lucia Zuin, Narayan Paturai também, and Jason de Souza was he's a chemist who introduced me to signal radiation, and we have some people who I have collaboration. So I thank you for your patience, and I'm ready to answer any question that you may have. Thank you very much.
Thank you, Antonio, for your excellent talk. And now I will open questions from the panelists. I will start with Gion Sil, because lady first.
Hi, my name is Jiwon.
It's Jiwon.
Yeah,
Camera,
I'm a
please,
lady. Okay.
Your camera, please.
I worked in synchrotron as well, but the
Yes.
Ultrafast is...
Sorry.
Hi?
Could you turn on your camera, please, because in order to show the public also, okay?
Okay, I'm shy, but...
Okay. You are very pretty, don't worry.
Okay. Okay? Okay. I worked in synchrotron, but I'm not familiar with ultrafast spectroscopy. So also, I'm not familiar with the dissociation. My question may be stupid, but I try to ask about something. Why do you interested in chlorine dissociation?
Okay.
I'm wondering why hydrogen or carbon it's not related to the dissociation, but only the chlorine.
Okay.
Is the dissociation.
Oh.
Yeah.
Okay. I thank you for the question. It's a very important question, and I have multiple answers for that. The first answer is physics. It's basically because chlorine is released in the atmosphere, and it depletes the ozone layer. So the main interest in chlorine is because it attacks, it threats the ozone layer. So this is the physical reason. But there is also another reason, which is experimental reason. My first measure at synchrotron in Brazil, we also try to measure the process in the carbon core. But there is a problem. I use the TGM, the toroidal grating monochromadour beamline, and there are some problems with the beamline in the carbon edge because it gets dirt because the carbon.
I know. Yeah.
And that's a limitation. So this is the limitation. Yes. Mm-hmm. In Canada, I moved to Canada. I used the PCM beamline, but the limitation was the photon energy. It only goes to chlorine. It does not reach the carbon edge, which is 300 eV. So it's another experimental limitation. So those are the reasons. Thank you very much for your.
Thank you for your answer. It's very clear. Thank you.
Thank you for your question. And now I will call, the question will be asked by Professor José Jesus from Germany. José?
Hi, hello. Thanks for the talk. Very nice. I'm not towards this area. I mean, this is totally different to my area. I'm more towards the solid state.
Jose, your camera, please.
My camera is on.
It's on. Let's see. Okay.
But I have a question. So you said that most of what you said in gas phase can be applied in condensed matter. How true is that? I mean, it's quite different.
I see. The process are the same. Well, I know, as I said, I'm a gas phase guy. I don't have much experience in the condensed matter, but I know some papers in the literature who they use Auger spectroscopy to study condensed matter using synchrotron. And the difference is because they don't use gas phase, they use a condensed matter, but they also study the same process, the Auger, the resonant Auger, and the normal Auger. So those processes can also be studied in a condensed matter context. But as I said, I don't know much about it. I cannot talk. I'm not aware of ultrafast dissociation in condensed matter, but I know that they can use Auger spectroscopy, resonant and non-resonant, in condensed matter. I can give you reference if you want. There is some people in Japan I know they use Auger spectroscopy in condensed matter. But unfortunately, I'm not an expert in those subjects, but I know that they can also study Auger spectroscopy to understand the dynamics of the dissociation, desorption of fragments from condensed matter using Auger spectroscopy. They can study fragmentation, selective fragmentation, desorption, and things like that. But unfortunately, I'm not an expert on those subjects.
No, it was just a curiosity because as a person working in solid state, we know that it's quite different than from gas phase. Yeah. I mean, gas phase is, I don't want to put it down, but gas phase to some extent is easier in some cases than solid state. Yeah, because in gas phase you can have calculations easily made.
Yes.
In solid state, the calculation breaks down.
But
Yeah.
Jose Antonio, I have an idea, because in condensed matter we don't study ultra-fast effects, because the measure of the effects in condensed matter occur in the region of Frank codon.
Okay.
Yeah, that's true.
Maybe.
Okay.
Okay. Jose, did you finish?
Let me see. There's a couple of questions. Some of them you have already answered. So probably I didn't understood. I didn't understood why does the forbidden transition happen in the SF6?
Okay. Good question. I think I went through it too fast. Okay. You mean this one? Huh? Okay.
So what is the origin of that transition? That's the thing I didn't got clear to me.
Okay. First, so the transition is a resonant transition from an occupied to an unoccupied orbital. And from group theory, we know that if the symmetries of the initial and final states are the same, the transition is forbidden, dipole forbidden, because of the symmetry, because the dipole operator is odd. So if you calculate the integral is 0 because the symmetries. So it's forbidden by dipole, but it takes place. It's very weak and it takes place. So what do you mean if it's forbidden? Why it takes place? Because when the transition takes place, the vibronic modes of the molecule are excited, and those vibronic modes change slightly the symmetry of the molecule, allowing this forbidden transition to take place. So it's a vibronic coupling. So it's called forbidden vibronic transition. It's a vibronic coupling that allows this transition to take place.
Okay. No, that's much clear. Yeah, we'll leave it like that at the moment. Yeah, thank you for the talk.
Thank you.
Thank you, Jose, for your questions. Thank you, Antonio, for your answers. And now I will call Professor Stewart. Professor Stewart from London.
Thank you, Antonio. It's a very interesting talk, and
Thank
it's a slightly different subject to what I'm used to.
Yeah.
Can I ask a general? I followed your logic. It's very nice. Thank you. Can I ask a general question? Could you apply these techniques to, say, pollution from cars? The big issue in England is pollution from cars, and maybe some nitrogen compounds due to combustion of diesel. Could your techniques be applied to these types of chemicals, the nitrogen-containing contaminants, perhaps?
Yes.
Would that be useful?
Yes, can be used, can be applied. We can apply it mostly all molecules in gas phase. You can use the same mechanism. So at the very beginning, I was not looking for ultrafast association. At the beginning, I was just trying to study the fragmentation of the molecules, how it fragmentation, because the fragmentation pattern may change the chemistry of the atmosphere. So the idea, my initial idea is just to study the fragmentation. And then I stepped and observed the ultrafast association, which was a very good, would call my attention. But yes, it can be applied to any molecule. And some molecules, in the case specifically of ultrafast association, some molecules may exhibit ultrafast association and some not. It depends, as I said, the time of association compared to the time of the core hole. So you have to have a very deep, very steep potential coverage, very repulsive just a moment here. The potential energy has to be very repulsive in order to increase the dissociation time. So the excited state that we see that they is supposed to be very repulsive, and a sigma character in a chemistry language, and the mass of the molecule have to the effective mass needs to be very small. So the dissociation time competes with time, the core hole time. Otherwise, you cannot see ultrafast dissociation. But those techniques can be used for any molecules, for ultrafast or not.
That's great. Thank you very much. And thank you, Antonio. I enjoyed your talk. Thank you again.
Thank you.
Thank you, Stuart. Thank you, Antonio. And the next panelist will be his questions is Professor Mário Reis. Mário?
Yes. Okay. Thank you. Thank you for this talk. I have only one question. It's a curiosity about the technique. Do the Auger electron have any kind of angular correlation? I mean, such as X-ray diffraction, for example?
Oh, yes.
It's only curiosity about the technique.
Yes. I have not measured the angular correlation, but yes, they do exhibit angular correlation. And in some case, yes. But the techniques I use, they cannot measure the angle of ejection angle. But yes, they do have distribution, angular distribution, which is not uniform. But it's not. But it's not uniform. But usually is not correlated with the photoelectron. If you mean that.
Yeah, because
there's no correlation between the. Okay.
Yeah, for example, perturbed angular correlation. If one photon has correlation with the previous one. I mean, there is some correlation with the emitted photons and X-ray diffraction.
Yes.
The angle has information about the material. And the angle has information about something about the material, as the previous question of the colleague, in condensed matter, the angle has information about the material in a certain level. My question is, if the Auger electron has a kind of information, what kind of information this angle can bring for us?
Okay. I think I understand. Well, the angular distribution of the Auger electrons and the photoelectrons, they depends on the polarization of the synchrotron photon. I only use linear polarized photons in the case, but it's possible also. And in condensed matter, I know they use it. They're circular polarization photons to study these angular effects. So I know that in condensed matter, they use a lot of circular dichroism to study these angular effects. But in my case, the techniques that I use, I cannot measure this distribution, unfortunately. But yes, they do exhibit, they do have this information, but I could not access it due to my experimental limitations. But yes, they do.
Okay, thank you for your answer. For your answer.
Oh, thank you, Mário. Thank you, Antonio. And Ximena, are you here?
Profesor Isaías, ¿cómo está? Profesor, también. No, pues en este momento no tengo preguntas. solamente pues la verdad es que es un tema bastante interesante. Muchísimas gracias por la charla. Revisando aquí en las redes de la universidad, tampoco tenemos preguntas del público, entonces muchísimas gracias.
Okay. Muchas gracias, Ximena. Before I finish our talk, I would like to remember that every Saturday we have a meeting for promoted by the Latin American LAFMAT, Latin American Physics of the Condensed Matter and Science, Material Science. Sorry, I don't remember the name of our network. But in the next talk will be Professora from Korea. I don't remember. Professora, are you here?
Jiwon Seo is her name.
Yeah, okay, no problem. Luis, do you have any words to talk?
Well, yes. Como habíamos mencionado, gracias Antonio Santos. Quizá puedas decir palabras de despedida para todos. No sé si tiene algo, no sé, tiene algo más que decir para hasta pronto o algo para o público que nos sigue, que es la red latinoamericana de física, materia condensada y ciencias de los materiales. In English is Latin American Network of Matter Condensed Physics and Material Science. We have a web page, LAFMAT.com.
Just a moment. Just a moment, Luis. I forgot the Professor José Fermi. José Fermi, do you have any question? Sorry, Fermi.
I cannot listen.
Can you hear me, Antonio?
Oh, okay. Now it's better.
How are you, Antonio? I have no questions for you. Thank you for your nice talk. Muito obrigado pela sua palestra.
Obrigado.
E parabéns from Venezuela. Grande abraço.
Okay. Gracias. And I apologize because as I said, I did not prepare my talk in English, so I improvised. So I apologize for that.
Don't worry. You spoke very well. Fermi, sorry again. So you have time to your last words, Antonio.
Me? I'm sorry.
You.
Okay. Oh, so I would like to thank you again, Zaius, for this invitation and see some people here and talk about a little bit about my work. So I wish you good luck. And also I will change to Portuguese. Eu acho que o Mário está aqui, né, com surpresa. Essa semana eu tive com uma senhora que disse que foi aluna da mãe dele. Então, um mundo pequeno.
Small word.
Eu não sabia.
Não, tá falando comigo não? Desculpa.
É o Mário, sim, o Mário Reis.
Foi?
Tem uma senhora que me encontrou, uma jovem, ela falou de você, né? E falou que foi aluna da sua mãe.
Pois é, para ver como o mundo acadêmico é pequeno,
tem muito aluno, né?
Pois é.
Mário, abra sua câmera.
Opa, eu abri o microfone, mas não abri a câmera. Pois é, você vê como o mundo acadêmico é pequeno, né?
Pois é, pequeno.
Pois é.
E ela falou que está saindo fora do Brasil agora, não sei.
Quem?
Você?
Não, por acaso estou em Portugal nesse momento.
Isso, tá. Ela falou algo assim.
Mas a minha mãe também, apesar de ser minha mãe já tem 82 anos, mas continua orientando, está sempre trabalhando.
Que legal.
É
um mundo pequeno, só uma curiosidade, foi um mundo pequeno.
Eu vou falar em português.
Ela falou de você.
Eu vou falar em português para ficar só entre nós três. Depois você conta sobre isso, tá? Everybody, now to everybody, if possible, open your camera to acknowledge the speaker.
Well, thank you very much.
Thank you, Antonio. Very nice.
Thank you.
Thank you very much,
again.
Antonio, for your very smart talk.
Gracias. Hasta luego.
Gracias.
Muchas gracias, Antonio. Muchas gracias.
Gracias.
Nos vemos el otro sábado.
James.
Hasta luego a todos, que estén bien.
Hasta luego. Feliz fin de semana.
Bom fim de semana.